Welcome. In this section, we'll go through the concepts involved in training a neural network and the problems faced. We'll also see how we can tackle these problems. Do you remember that we have a method for training machine learning algorithms? It's gradient descent, an iterative training algorithm which optimizes the parameters. But why can't we use this algorithm in case of neural networks? The problem is that even for a small neural network, the number of parameters are extremely large. It is practically impossible to use gradient descent in such large dimensions as it takes longer time and compute. But it also fails to converge in such a complex space. Fortunately, we have been gifted by a algorithm called backpropagation. The backpropagation algorithm works by computing the gradient of the loss function with respect to each weight by the chain rule. Compute the gradient one layer at a time and iterating backward from the last layer to the first layer, and hence the name backpropagation. This is considered to be an example of dynamic programming. Hold on. Is the problem solved? Everything can't be easy. There are some common problems faced by a neural network in the process of training. Some of them are vanishing gradients, exploding gradients, overfitting, and non-convergence. Let's see one of them. The first major problem in large networks is vanishing gradient problem. We saw that there involves a multiplication of gradients from the top layer with the derivative in the current layer. In this process, if these gradients are very small, like less than 1, on successive multiplications, the value of the total gradients become very small and become insufficient to update the parameters in the beginning layers. This problem can be solved by using a good activation functions like ReLU, which stands for rectified linear unit, at every layer of the neural network. These activation functions have the capability to generate large gradients, hence avoiding the diminishing of gradients. Good loss functions might also help, like the mean square error. Another similar problem is called exploding gradients. Instead of the value of gradients being too small, here the values blow up, which are greater than 1. This problem is very simple to solve and is generally solved by clipping the value to a certain limit. Another common problem is overfitting. As you know from machine learning, overfitting is a problem when the network or the model tries to memorize the data. Neural networks have great power. Under high training, they can overfit any complex curve, as you can see in the figure below. This problem can be solved by 4 major approaches. One is early stopping. When we see that the training accuracy exceeds the test accuracy by a large amount, or when the test accuracy starts dropping, we can say that the models have started overfitting and we can stop the training. One approach is to use dropout. In this process during training, we ignore some of the neurons as if they were not there. This gives a regularized effect and reduces the interdependencies between the layer, which is a drain for overfitting. The third method shows L1 regularization as in machine learning, which is added to a loss function and penalizes the parameters preventing overfit. The fourth shows L2 regularization, which is like more squared version of the L1, saves the same purpose. The next basic and most foreseen problem is the non-convergence of the algorithm, like the dead gradients and stuck at low-cut minima. There are many complex mathematical theories explaining the non-convergence but are not fully proven. But experts recommend 2 popular ways to define this. The first one is batch normalization. Batch normalization converts the output from each layer to a standard distribution with zero mean and unit variance, making the job of the next layer easy to train and infer. This process is proved to be very helpful, especially in large networks, as it makes training robust and fast. Initial weighting methods also have an impact on the training. If we use 0 or some constant initialization for all the parameters, they all update together with same values, resulting in the collapse of the network. Methods like Xavier and H initializations prove to be having good results. So we have gone through a lot and let that sink in well. Thank you.